from the Instituto de Astrofísica de Andalucía. Today is our pleasure to have with Dr. Tarek Hassan from the CMAT, who will be talking about sub-milliarcsecond resolution astronomy with Imaging Atmospheric Cherenkov Telescopes. Tarek will be properly introduced by Ruben.
Okay, so Tarek, I met him many years ago. We started actually the PhD at the same time. He did the PhD at the Universidad Complutense de Madrid, working for the CPA consortium. And then he moved to E5 for a postdoc. He got a Juan de la Sierra fellowship over there, stayed for a couple of years, and then moved to DESI, where he did a 3-year postdoc working in VERITAS, that is another Imaging Atmospheric Cherenkov Telescope, to come back later to CMAT in Madrid, in which he got one of these Atracción de Talento fellowships. And he also, since a few months ago, he was awarded with an ERC starting grant called Microstars, if I'm not wrong with the name, and that he will be starting in a few weeks, right? Yes. And we invited him here today because Tarek, apart from the general expertise that he has in gamma ray astronomy and imaging atmospheric Cherenkov telescopes, he actually also has some expertise in optical astronomy being done with these telescopes, and this is what he will be talking about today. So please, Tarek.
Thank you, Ruben. So I hope everybody can hear me well. I'm Tarek, nice to meet you. Okay, so IACTs means Imaging Atmospheric Cherenkov Telescopes, so these MAGIC telescopes that we have. And I will be talking how can these telescopes perform sub-milliarsecond measurements in several ways. Okay, so please bear with me. I will be talking about some topics that probably many people here know more than me. So if I say something wrong, I apologize. Okay, so you're probably aware that stars are enormous. Okay, so it's good to begin at my level. So so yes, stars are big, but they are very far away. Okay, so the relative distance between stars is enormous. Therefore, the actual angular size of individual stars is actually really small. Okay, and knowing how small these stars are is actually very important for astronomy. Okay, so having a direct measurement of the actual size of stars allows rather than direct a measurement of the luminosity, and this is actually very used in many fields of astronomy. So especially on ensuring that the stellar models that we use are correct. The only way, actually, stellar models are fitting actual measurements. So we need those measurements in order to ensure that the stellar models that we use in many fields in astronomy are right. Okay. So other very obvious uses of measurements on stellar diameters are right now a hot topic, are reconstructing the physical parameters of exoplanets. No, so when we see a transiting exoplanet, we know very well the properties of the star. Then we can actually improve a lot the transiting exoplanet analysis, and therefore infer stronger conclusions over the physical parameters of planets. But when we talk about milliarc-second resolution, what we really mean with that? So these are very small units, no? So I always start by assuming that the planet is flat, and just imagine that you are staying in New York, looking to the Eiffel Tower in Paris. Okay, so if someone was holding a €2 coin at the top of the Eiffel Tower, that would be 1 milliarc-second as seen from New York. Okay, this means that 1 milliarc-second is something very small, very small. Okay, and if now we stop talking about Paris and we start talking about astronomy, then the usual angular scale of the objects that we see when we look to the sky So the sun and the moon are roughly the same angular size, which is roughly on the tens of arc minutes. Okay. Then the local planets are at the tens of arc seconds. But then, apart from local planets, already the largest stars are already measured in milliarcseconds, okay, in tens of milliarcseconds. But when you look at the sky, most of the stars that you see with your eyes, they are already in the milliarsecond level, okay? So either milliarsecond, of course, some of them will be larger, as the ones that I'm showing here, but the typical size of a star, of the very bright ones, are milliarcseconds and obviously below, okay, and much smaller angular diameters, okay? And this is a figure that I will be showing many times during this talk. It's a complex figure because it shows both radio and optical, and in the y-axis, the angular resolution that the different instruments in the field have, okay? I'm sure many people here have experience with radio interferometers, but here, for example, you can see the Event Horizon Telescope, the resolution that is reaching the tens of microarcsecond resolution. You can see that the EVN VLDA network is here. You can see VLA, ALMA, etc. But here, starting at the center of this plot on the left, now we are talking about optical interferometers. Okay, so you can see here CHARA, VLTI. These are the famous ones. I'll be showing this plot a lot, just for you to be to put our results in this context. Okay, so the message that I want to send through is that Cherenkov telescopes are actually capable of performing sub-milliarsecond resolution measurements, and we have been able to do it in two different ways. First, interestingly, by measuring asteroid occultations, and second, using these telescopes as optical intensity interferometers. Okay, so first I will introduce very generally what are Cherenkov telescopes, but also seen as an optical astronomer, right? So here, for example, there is a picture of the first large-size telescope prototype, which is LST-1. Here you can see that the camera was not installed there. This is an old photo, but you can see that the structure of this telescope, the big reflecting dish, the arc holding the camera, etc., is really not that different as, for example, here there is a sketch of the Subaru telescope. It's really not that different. Okay, the Subaru. I'm specifically using the Subaru telescope because it's a telescope that has actually a slot for having a camera in the primary port. Okay, so Cherenkov telescopes are generally used to this. I mean, you have probably seen many seminars about this. So they are used to actually study the very high energy regime. Okay, so in the electromagnetic spectrum, they are focusing on the very highest energies of gamma rays. And how do they do it? So when these gamma rays hit the atmosphere, they produce a shower of particles, and these particles, they emit Cherenkov radiation because they actually go faster than the speed of light in the medium. But this Cherenkov radiation is blue. Therefore, Cherenkov telescopes are optical telescopes. Here you can see an example. This is MAGIC, this is HESS, this is VERITAS, and they are all measuring blue optical photons. Okay, so they are optical telescopes. The only, quote, only, which is enormous difference, but the only difference is that normal optical telescopes, they focus on directly measuring the photons that they want to study, like galaxies, spectra, etc. While what we do is study the sources that we study indirectly. Okay, so we record these blue flashes of light that last few nanoseconds, and then we reconstruct the original gamma ray and its direction, its energy, etc. So, but what makes Cherenkov telescopes what they are is the fact that they are optimized to measure these nanosecond scale blue flashes, instead of optimizing it to actually have excellent angular resolution, to reconstruct the galaxies, etc. So Cherenkov telescopes are optical telescopes with the only tiny difference that they are optimized to measure nanosecond scale blue flashes of light. So this is an example of a Cherenkov telescope. This is VERITAS. So I apologize because now I'm a MAGIC member and many people here are MAGIC members. But this is just an example of what a Cherenkov telescope is. They are large. They are actually very large in diameter. The VERITAS telescopes have 12 meters in diameter. MAGIC has 17 meters in diameter. And the large size telescope that I showed before has 23 meters in diameter. Okay, their field of view is enormous. How enormous? You can see it in the next slide. So these are the kind of images that we record. This is a Cherenkov shower. Okay, so these are the kind of images that we take and that we reconstruct its direction, its energy, etc. But to me, the interesting thing as an optical astronomer is that roughly the angular size of these images is comparable to the size of Andromeda, of M31. No? So again, if we go back to the Subaru telescope, we can see that the Subaru telescope on a single snapshot is also able to take the full Andromeda galaxy. Okay, and of course the Subaru telescope costs like 2 orders of magnitude more than our telescopes, and you can see it in the image. No, so roughly the image that we would see is something like this. I actually computed this properly, so I did a Gaussian smoothing, and this is what a Cherenkov telescope would actually see with our very large pixels. So we have very large pixels and a very bad optical quality. The bad optical quality means that our telescopes are cheap, and therefore we can make them very big. So a few technical details about our telescopes. So we use photomultiplier tubes, which are the pixels that we can use to actually measure nanosecond scale flashes, right? So this the electromagnetic showers that we want to record are not super bright. Therefore, we need very large telescopes to actually being able to collect enough photons during the short bursts of light that we go for. No? But no high angular resolution is needed. So the mirrors that we use are actually not astronomical quality as those of the GTC or other optical telescopes, and therefore they are much, much cheaper. So if you think of these telescopes as optical telescopes, they will never be able to compete with a telescope equipped with a CCD camera. Okay, so not only the noise that you will get into that CCD camera is much better, and as our angular resolution is terrible, then we will never be able to compete with CCD cameras. But there is a specific parameter space in which we do compete, and that is for very short observing times. Okay, so as probably some of you know, CCD cameras normally are not suited for millisecond scale measurements. We have, for example, in the Grand Tecan Hypercam, which actually allows you to go to the millisecond regime. But this is rare. There are not many optical telescopes equipped with very fast CCD cameras. And the faster you go, the sensitivity starts to be limited by the scintillation noise. Okay, and scintillation is mainly improved by having large telescopes. So our telescopes, even if they do not have CCD cameras, our photo detectors are not great as compared with CCDs. If we talk about very fast phenomena, then we start being competitive. Okay. So I will briefly talk about asteroid occultations and how we use asteroid occultations to do submilliarsecond measurements. Okay, so what is an asteroid occultation? So you first need a star, you need an asteroid, and you need an observer from Earth. Okay, so when there is nothing blocking the view to that star, you are measuring a constant flux of light. But when the asteroid passes exactly in front of the star and between the star and the observer from Earth, then you see that the light from star is blocked, and the only light that you see is that of the asteroid. And of course, it is not in scale. And when the asteroid moves away, then you see again that the flux goes up. And these asteroid occultations can actually be predicted. So we know the ephemerides of the asteroids. We actually compute what will be their path over the sky, and when they pass in front of a bright star, then it starts being interesting for many reasons. No, some of the reasons of why these events are interesting are this kind of asteroid tomography. So if you have many telescopes along the shadow of the asteroid moving over the Earth, then you are able to reconstruct with very high precision the shape, the position of the asteroids, and this has classically been done by amateur astronomers. Sorry, but there are results of actually very high impact, and people here at the IAA know this very well. So this is actually José Luis Ortiz is from this institute. I don't know him, so I don't know if this is here. But sometimes these events are extremely interesting. Okay, so when a Kuiper belt object passes in front of a star, then we can study Kuiper belt objects which are extremely dark, etc. Sometimes we find rings in these objects which have strong implications in the formation process, etc. So what we thought for observing these events is that they are faster than, for example, planetary transits. And because they are faster, then we are more competitive. No? So, yeah, these events are generally not followed by enormous telescopes. And Cherenkov telescopes are indeed very big. So they will provide good millisecond sensitivity, and we could see perhaps atmospheric profiles, rings, or something that we were not expecting. No? So for example, I can show you that this is the occultation that we were expecting for the first observation that we performed, and this is what we detected. Okay, so this is with VERITAS telescopes, which are 4 different telescopes. Okay, so here you can see the ingress, so when the asteroid blocks the light of the star, and the egress, which is when the asteroid moves away. You can see here all this pattern is maybe a bit less than 100 milliseconds. Okay, so this is something that occurs very fast, and here you can very clearly see a diffraction pattern. Okay, so we knew that this would happen. Okay, so this is something that you expect. But why do we see such a clear pattern? Okay, so why isn't the noise diluting this signal? So again, the main source for noise when you are observing very, very fast optical measurements is scintillation, is the atmosphere. So you can imagine that the light from a star is actually similar to the light on the bottom of a pool, this typical pattern of light going up and down. So the larger your telescope is, the better the measurement of the average of light that goes inside your telescope, right? So the atmosphere does something very similar. So the larger your telescope is, the less scintillation you have. No? Also, having multiple telescopes allows you to measure the same thing as they are separated for 100 meters, then allows you to observe the same thing, because they are not observing the same atmosphere, only the very, very higher atmosphere. And therefore, you have several independent measurements from the same thing. So this is the data that we got for the first occultation that we measured. As you can see, the error bars are super tiny. The data set was fantastic. And you can see that there is a difference between this blue dashed line and the orange one, okay? And the blue dashed line is the pattern that we would expect for a point-like source. And the one that we see in orange is the one that would come from a disk of 0.1 milliarc seconds. So we are talking about a tenth of a milliarc second. So it's something, a tenth of a €2 coin in Paris, as seen from New York. Okay, so this is something very, very small, and this was the first time achieved in the optical, as far as we know. Maybe some old paper or something. So you can see that all the measurements from the independent measurements that we took from independent telescopes agree very well. And we repeated the observation. We saw another occultation, and again, we were able to detect the angular diameter of a star, in this case, 94 microarcseconds. Okay, to put this into context, again, measurements agreed very well. And just to put this into context, the first shadow of a black hole that we measured, this is 50 microarcseconds. And the star that we measured is this size, okay? Of course, our resolution is not as good as the Event Horizon Telescope. Of course, I'm not claiming that, but just to say that this was achieved in the optical, okay? This was a first. So just for you to put things into context, here you can see the measurement from the Event Horizon Telescope, and here you can see the 2 measurements that we did with Cherenkov telescopes. And this is the actual size of the spot size of those stars, okay? So The optical PSF of a Cherenkov telescope is this big, is the size of my fist, while the measurements that we were able to do is 7 orders of magnitude smaller. So the grant that I just got plans to exploit this millisecond sensitivity for another scientific objective. No? So as we were talking before, that these asteroid occultations may be very interesting when you're observing Kuiper belt objects. The Kuiper belt objects are the remnant of these protoplanetary disks that we see in young stars. Okay, this is imaging radio, for example, by ALMA, and we see that the planets are forming here. And when these systems cool down and evolve, we see something similar to our own solar system. No? So here we have the planets that accreted most of the asteroids in the inner region of the solar system, but the Kuiper belt objects are a remnant of these protoplanetary disks. And it did not undergo such a collisional history so that most of these asteroids were destroyed. This means that by studying the Kuiper belt object, we may infer conclusions on on how planets were formed, essentially. You know? So on how objects start gathering material, etc. This is one picture in which I show the radius of the Kuiper belt objects known. Okay, here we have many objects. So these are objects that are very far away from the sun. It means that they are not very bright. They are very, very, very dark. Okay, they are not, of course, they are not hot. So therefore, they barely emit light. They only reflect the light from the sun. But as they are very far from the sun, they barely emit any light. No? So here we have detected many of them because they are large and therefore deep observations, you can actually measure them. But when you start talking about small Kuiper belt objects, we barely have detected some of them. Okay, most of these are upper limits, but these are a couple of detections of roughly kilometer scale asteroids. Okay, what our predictions seem to suggest is that by searching a bright star at the right location and simply waiting, over tens of hours of observation, which probably the people having experience with Cherenkov telescopes know that it is not that much time. So normally our observations tend to go 50 hours per year and things like that. So if you just wait, a tiny object of 100 meters, a Kuiper belt object of barely 100 meters, would produce such a signal over a MAGIC telescope or over the LST-1 telescope. Okay, this means that it seems reasonable to think that over reasonable observing times, if these telescopes had the capability to actually perform clean, fast optical measurements, then we would be able to put constraints on the sub-kilometer population of Kuiper belt objects, and this has implications on how the solar system was formed, okay? How planetesimals were generated.
Is it okay if I interrupt you?
Please do.
Cool. So I see this is a 9th magnitude star, so absolutely fantastic. Of course, then I wonder about the statistics, but probably you're going to get there, right?
Which statistics?
I
will not get deeper into this. So,
but I guess you get there, right?
You mean the statistics?
If I point to a random 9th magnitude star, there's not many on the sky there. I don't know, 9th magnitude, maybe a million or so.
This is a star that I handpicked from Gaia. So this is a true star at the right location.
So you picked this star and you knew something was going to happen, or you just picked it and looked?
I picked this star because its angular diameter is super small. This is an O star.
You did not know that an occultation would occur?
No.
Okay.
No, this is not data. This is a simulation. Sorry. I wish this was data.
The probability would be of a Kuiper belt object passing in front of a 9th magnitude star.
Exactly. That is something that we expect to happen over 8 hours of observing time. 8-10 hours. Of course, this depends. Do you want to say something? So it depends on the sensitivity that we reach. And as we need to upgrade our hardware, then this is certainly not something. Yes. So, but if we reach if we reach the point in which scintillation is not really an issue, and we start being limited by the shot noise, and I remind you that as our pixels are very large, we are limited by the shot noise because we are integrating a very large field of view, then we would expect, if our theories are right and our formulas are right, to have one event per 10 hours.
Wow. Okay, thanks.
Why? Because we have several telescopes. they are separated, and therefore you have independent measurements of this noise. No, so
no, I'm not wondering about the noise technology, just about the probability.
Yeah.
Passing in front of a star.
Yeah, this was also my.
So because that is my main thing, because I'm not worrying about the detection. I believe everything technically. I just wonder, I mean, are there so many capable objects around that you have a significant probability on a very large sky that one of these things passes right in front of a 9th magnitude star? That was my worry.
Yeah, this strongly depends on exactly this. Okay, so if these detections are right, be aware that these are low significance detections. Okay, so there have been several detections that have been hinting towards having a sub-kilometer Kuiper object slope that is roughly of this factor Q. This is a Q roughly of a value of, I remember, like 4 or 2.
What is the cyan line?
This one I will explain now. Yes. So this cyan line is the population of Kuiper belt objects that you infer from the cratering records of faraway minor planets. So this blue line, by imaging the surface of Charon, counting the amount of craters that they have and the size of the craters, then you simulate it, and then you infer what is the population of small objects. And there is a very clear difference between what you infer from the cratering records and what several experiments are claiming to detect. So to your question of the probability, if these experiments are right, and here we have a power law, then the lower objects you search for, so if you are sensitive to tiny variations in the flux of the light coming from the star, then you start having many events. If you, for example, if we only had GTC, then the individual noise added by the scintillation of a 10-meter telescope then already dilutes that signal. But if you have several, you have excellent signal to noise, then you start getting to smaller and smaller objects, which become much more frequent. Okay. There are, of course, 1,000 parameters that get into this equation, and therefore the uncertainty is very large. Okay. So, but what we believe is that by having a multi-year proposal observing good candidates of stars, then we would put upper limits that would essentially put in question these measurements. The other method that we have used to perform sub-milliarsecond measurements is using these Cherenkov telescopes, and this is a render of how the Roque de los Muchachos will look like after the CTA Observatory North Array will be built. And it just reminds you to radio telescopes, right? So there is a technique that actually allows you to use these Cherenkov telescopes as interferometers, very much like, for instance, the ALMA telescopes here. So going back to this image that I have been showing again and again, we now focus on the optical telescopes. Here you can see CHARA and you can see the LTI. But you can also see this NSII, the Narrabri Stellar Intensity Interferometer, and I will be focusing on this one right now. Okay, so maybe this is not needed, but let me give you a gentle introduction to interferometry. This is something very hard to understand. For me, I can barely understand it, but it will be just very superficial. I know that many people here have experience with interferometry, so probably this is not needed. But the way that we generally explain what interferometry is very simple. Okay, you have individual telescopes, they have a set of independent qualities, but if they work together, and technically you are capable of making them work together, then they work as one and they improve their resolution. Okay, so here there is a sketch of the Keck telescope. No, each of them is a 10-meter telescope, but when you combine the light beams and they operate as an interferometer, the actual limiting the resolution that you have is that equivalent of an 85-meter diameter telescope. Okay, so interferometry allows you to break that diffraction limit of a single telescope and improve the resolution of the telescope. But it has certain problems associated, so it's not as simple. But the main explanation of how they work is essentially that these instruments, what they measure is an interference. They measure a very tiny signal that is hidden in the electromagnetic waves that different telescopes detect. Okay, so the way in which you measure this interference, it's very different in radio, in optical, and in optical there are several ways of doing this. No, but something important to remember is that some information is lost in the process, and in our case, most of the information is lost in the process. So as I was saying, there are several methods to measure this interference, and optical interferometers, what they currently do, all optical interferometers right now in the world, or most of them, they physically combine the light beams. Okay, so you have light coming from one telescope, light coming from one telescope, you physically combine them, and the interference seen when combining those two light beams shows what I'm calling here interference. Okay, it's much more complex than that, but please bear with that. Radio telescopes, as you probably know, they are only linked electronically, and that's why they have been so successful, because it's way simpler. So optical interferometers, they need to control the precision that they need on the whole path of the light, meaning like mirrors, every single reflection that you have of the light beam needs to be controlled with a fraction of a wavelength, meaning that if you are observing blue light at 300 nanometers, then you need to have a precision of tens of nanometers. And that is hard, as you can imagine. And building a very large optical interferometer, having it controlled the path of each individual photon to a precision of tens of nanoseconds is expensive. That's the problem, that is very expensive. Okay, so this Narrabri stellar intensity interferometer was actually the first interferometer ever built, which is funny. And it's a technology that was essentially lost. Why was it lost? Because it has some flaws, some problems that were too complicated at the time. But these were envisioned by Hanbury Brown and Robert Twist, and they developed the Hanbury Brown and Twist effect, which is something very complicated to explain related to the photon bunching of photons on their way to Earth. But just for you to see how these telescopes were built, they were 6.5 meters in diameter, quite large for the time. This was done in the 60s. And one very fast optical detector here, one photomultiplier tube, okay? And the main difference between this interferometer and the optical interferometers that we were talking about is that they are only connected electronically. So what you are correlating is not the actual phases of the beam. What you are correlating is the evolution of light intensity versus time, okay? So it's a correlation in time. And they were able to measure the angular diameter of 32 stars in the 60s, okay? And this was a great achievement. This was impressive, okay? But intensity interferometers have very strong limitations that essentially made this technique obsolete, and now classical optical interferometers started improving the sensitivity of intensity interferometers, and they dramatically improved them. No? So these telescopes have several problems. They require enormous reflecting surfaces because they need very high statistics of photons. They require extremely fast electronics that at the time was extremely hard to achieve. Okay, now it would not be a problem, of course. They have a strong phase information loss. For those that know interferometry, they completely lose the phase information of the signal. They measure V squared, the visibility squared. Therefore, any complex component of the Fourier space is lost. But then they have some strong advantages over the classical optical interferometry, which is, as they are only connected electronically, you can have as many telescopes as you want. Okay. Also, as separated as you want. And also, they are insensitive to atmospheric turbulence. And this is a strong plus. Why? Because if you need to control, as I was saying before, the path of photons with a precision of tens of nanoseconds, the atmosphere itself is already adding it's already breaking the possibility of having excellent precision for blue photons. No, that's why generally optical interferometry is performed in the infrared, or over long baselines, over long wavelengths. So generally in the red. Okay. Okay. So how about IACTs? These telescopes really look like Cherenkov telescopes. Okay. So in the case of Cherenkov telescopes, we already have enormous reflecting surfaces. We already have them. Okay. So we don't need to build anything complex. And the electronics are already at the gigahertz level. So the technical capabilities of our telescopes really match the technical capabilities of the Narrabri telescopes in the 60s. Okay, so our predictions originally was that with the MAGIC telescopes, if they were able to perform intensity interferometry measurements, they would allow us to go farther into the blue. We would have similar resolution as Chara in the blue, and we would improve the sensitivity of the Narrabri stellar intensity interferometry by a factor 10. Okay, just playing with the numbers, we should improve a factor 10. No? But the truly exciting thing to consider is that if we actually demonstrate that this is possible, and we will be soon be building up to 100 telescopes in the southern array of the CTA observatory, if these telescopes were slightly modified to actually allow these optical intensity interferometer measurements, you could have the first kilometer scale optical telescopes of the world. No? So also something quite interesting that I always find very amusing is that these observations are possible under very high moon scenarios. Why? Because they have a very narrow optical filter in front of them. So we would not even compete with the observing time of the gamma rays. So we would not harm the CTA observatory at all, while we could answer many questions in the stellar astrophysics field. No? How would such a telescope, what would be the resolution of such a telescope? So we would improve a factor 20 the resolution of Chara. We would go farther to the blue, but also something very important is that the UV coverage, this is the spatial scales that the interferometer would be studying, okay, would be so dense, so you would be measuring so many different scales simultaneously that the actual amount of detail that you would be able to reconstruct from stars would be enormous. Okay, this is of course a simulation, and here, bear with me, this is ignoring the signal to noise. This is just showing what would be the reconstruction of the sun, of our sun, if it was a 0.5 milliarcsecond star, and every single correlation here had excellent signal to noise. This is not realistic. This is not a realistic simulation, but shows what kind of resolution we would achieve, which is incredible. So is this possible? The answer is obviously yes, because we have already done it with MAGIC. Okay, so in MAGIC we did a very rough modification of the setup. So essentially we put here a very narrow optical filter in front of a single pixel of the MAGIC cameras. Then we built a correlator with an oscilloscope, and then we did a fast publication in 2020, and we demonstrated that MAGIC indeed reaches a sensitivity of a factor 10 the Narrabri stellar intensity interferometer.
How deep can you go? What's your stellar magnitude?
Wait. This is the first question that people.
If I walk out, it's not because I'm mad.
It's fine. It's fine.
This is why I'm asking this question.
It's fine. So it's right now. I need to apologize because the Narrabri stellar intensity interferometer had really very strong limitations. Okay, so this factor 10 seems amazing, but the limiting magnitude roughly right now with only the two MAGIC telescopes is roughly magnitude 4 in B. So it's really not that great. But the thing is that the bottlenecks for improving this are very simple to remove. No? So there is really a long gap of improvement. Okay. So these are, for example, some preliminary results with a more mature setup that we have now. So all this hardware is already not used in MAGIC. So we have very much upgraded this. I did not bring many pictures, etc., because it's not published yet, and there will be a performance paper soon about this. But here are some preliminary results of these are the stars that we consider calibrators. So they were directly measured in the past. and we are already reconstructing their diameter better with very short observing times. But also the stars that we call candidate stars, so those stars that do not have a direct angular diameter measurement, and at least the predicted diameter matches very well the angular diameters that we are reconstructing. Okay, so this is a very preliminary analysis. We are improving it every day. We are not stellar astrophysicists. We are not interferometry experts. Therefore, we are advancing slowly. But we are already seeing that that the system works. Okay, so they are still not very sensitive. Okay, so the limiting magnitude is roughly a fourth magnitude. But MAGIC has demonstrated that these Cherenkov telescopes can indeed become competitive optical interferometers, and there is essentially no limitation to how many telescopes you can add to the. There are even ideas of building the whole Roque de los Muchachos, even with GTC, even with other optical telescopes, to actually put them within the network. No? So this is perfectly possible. So these are already my conclusions after 40 minutes, which is we know that Cherenkov telescopes have achieved amazing things over the last 20 years as gamma ray telescopes, but interestingly, they are also competitive as optical telescopes in a very particular time regime, which is for very, very fast phenomena. In millisecond timescales, they can be competitive. We are, of course, less sensitive, but the signal to noise that we may achieve is even better than that of, for example, of the Gran Tecan with hypercam, if the object that you are studying is bright enough. And therefore, we believe that they may be competitive for studying the sub-kilometer Kuiper-Belt object population, but also as optical intensity interferometers, they also may dramatically improve the current generation of optical interferometers. We will never be as sensitive as, for example, of VLTI. It's impossible. We will never be as sensitive as them. But VLTI has an angular resolution of 2 milliarcseconds. If you want to go deeper, if you want to go to better angular resolutions, then you need telescopes that are much farther away. And building optical interferometers much farther away is very complicated and very costly. While these Cherenkov telescopes already exist, and upgrading them is not that complicated. Yeah, and they actually have very interesting potential in the field of stellar astrophysics, mainly on the OBA stars, because they are bluer and because our photosensors are blue. If we upgraded them, there is nothing stopping us for going also to the red. But as generally OBA stars are the ones that have a smaller angular diameter, these are the ones that are in our sweet spot, let's say. And this is all.
Thank you very much, Tarek, for the comprehensive talk. And now questions. Okay.
Yeah, I would like to know which is the photometric precision that you can reach when you are, for example, doing some occultation that you have shown before. So can you go before to the slides where you were showing the transit or the occultations of the asteroids?
So you mean what is the precision for actually measuring?
Well, you can translate this is you can translate this in photometric precision to see which is the millimagnitude you can see in the depth of this occultation.
Yes.
So which is the limit that you have?
So generally, right now we are observing more and more occultations, and generally we stop observing them with the current setup and with MAGIC, 12th magnitude stars.
No, but then, okay.
So 12th magnitude stars, the pattern that we see is already very noisy, and we assume that we will not really extract many conclusions. You mean what is the minimal difference that we can actually measure? That is very complicated to answer, because the actual difference that we can measure over millisecond timescales,
yes,
that we could, I believe, we made a paper, for example, putting constraints on the optical emission of fast radio bursts. So these are millisecond emission timescales, and the limits that we put there are on the 13, 14 magnitude level, but depending on the time length of the event. No, but they are on the 13, 14 magnitude level with MAGIC. If you have, for example, the LST, those will significantly improve. Okay, but for example, if you ask me what is the maximum difference in flux that we would be able to measure.
But the minimum.
The minimum, yes, sorry.
Is important.
The minimum. Going from a stable flux to a stable flux is much more difficult. Why? Because what we are good is at actually the transient signal, but actually measuring a stable flux is very complicated for us because we have a certain degree of systematics on the amount of light that we measure in the camera, etc. We are good at measuring relative fluxes, not so much like absolute fluxes. For example, for planetary transits, we are not that competitive. Why? Because even if, in theory, we should be able to be awesome, we would essentially need a different camera. We could think about building a big CCD that stored over longer timescales, and then we would start being competitive. But with photomultiplier tubes, we are not competitive. It's very hard to measure a stable flux of photons.
But with an exoplanet, you should also be able to see
The shape of the transit.
The dip.
Yes, but it is much slower. For an exoplanet, you would see it, but it is much slower. Therefore, all the problems that our pixels have over long time scales, you start eating them, and then the calibration is complex, it's complicated. But this is something that has not been really actually investigated thoroughly. So actually getting some people actually exploring this possibility is something that definitely would be worth. Actually, there is a paper. Its title is Cherenkov Telescopes as the first. It was a paper done like 20 years ago by Brian Lackey, if I remember right, explaining what is the limit of precision of Cherenkov telescopes for actually measuring, for example, exoplanet transits. And in principle, it should be good, but I can tell you that with PMTs it will be hard.
Okay, so we can forget about the idea of cover a full transit because it's not that good, but we can focus on particular points of the transit, for example, the ingress or the egress, to search for some particular features.
Yes, and this could be certainly possible, especially for those that are relatively fast. I would believe that it could be something that could be achieved, and the noise that we would have coming from the atmosphere, etc., is very small if the star is bright enough.
What about using other types of detectors like silicon PMs instead of PMTs?
Or a CCD camera.
Yeah.
Just a CCD camera. Just put a big CCD camera.
Or telescopes are equipped with PMTs, but the future ones, some of them will be equipped with silicon PMs.
Yes. So
have a lower noise.
Yes. So maybe. Maybe silicon PMs are, because silicon PMs, if you reach the photon counting regime, then in principle it should be simpler to have like an absolute flux. With photomultiplier tubes, there is this problem that it's an analog signal that is hard to actually say how many photons you are measuring at which time. No, so you see this pulse. It may be 1 photon, it may be 2 photons. It is also possible, if the rate of photons is very low, it is also possible to actually count, but with silicon PMs it's much easier. So that would certainly be a possibility.
There's something I'm not sure I understand. You said at the beginning that the field of view of this telescope is big, right? So and what you're showing there is like the integrated blocks in all of them? It's
just 1 pixel. So we are not using the full camera. We are just focusing all the light. The best picture is probably this one. So it's something very similar to this. It's just a single photomultiplier tube that is channeling all the photons that we receive from a star. Okay, here you can see it. So this is a set of optical filters that were done for performing moon observations for gamma ray observations. Okay, so this is not related to our science case, but this optical filter there is the one that we are using. So it means that we are not using the 1,000 pixels that we have in the camera, just one. Then with the mirrors, we focus all the light on a single pixel, and then we do science with just that pixel. So you just channel the signal of that pixel, you channel the signal from another pixel of another telescope, and then you measure the tiny correlation that you have between the yes. So in our case, we can only do intensity interferometry. So measure very fast how intensity evolves. And then there's a tiny correlation when you compute the correlation of the two pixels.
The angular size is not 3.5 degrees anymore, but 0.1 degrees. That is the size of one pixel.
Exactly.
Okay, there are two questions in Zoom. So Miguel Pérez Torres, please open your mic. Go ahead. Miguel, we don't hear you.
Okay, sorry.
Now we can hear you.
We could, but not now.
We have an okay.
Miguel, are you still there? Okay, in the meantime, maybe Benito, if you can open your microphone.
Yeah, okay. Thanks for the talk, Tarek.
Hello, Benito.
I had a question I think you didn't mention, and it's basically, I think, my lack of fully understanding the system. But when you get the observations, because especially for the Kuiper, you will be focused on the galactic plane, I imagine. Then don't you have confusion with many stars within the field? Like the signal that you capture is actually from many stars there?
Yes. So actually, the direction in which we need to look at is not the galactic plane, it's close to the ecliptic. Okay, so it's not exactly the same. And so there is a long list of requirements for the candidate star to be ideal. Okay, so it needs to be in the anti-solar direction because Kuiper belt objects are moving faster in that direction. I did all these calculations quite some time ago, so I apologize if I make a mistake. So it's essentially anti-solar direction so that the Kuiper belt objects are faster. Then the density of the Kuiper belt objects is higher, close to the Lagrange points of Jupiter. Therefore, it would be ideal if you observe into a given direction. Then it needs to be very close to the ecliptic, within ±5 degrees, because the density of Kuiper belt objects will be higher there. So there are many constraints. But I can tell you that the 9th magnitude star that we found was quite clean, the environment. Okay. We could also go to slightly brighter stars, but their angular diameter would be larger. And the signal that I was showing, as you can see, is not a complete occultation. Why? Because the Kuiper belt objects at those distances, so a 100-meter object at 40 astronomical units does not block fully the light of the star. Okay, so what you would see is a tiny variation of the flux. No? So the smaller the star is, the more clear the diffraction pattern will become. So we have certain freedom on choosing a star, but this specific star that I found is good enough as long as its angular diameter is what we predict. But of course, nobody can assure that, right? So maybe we would need an optical interferometer that has excellent resolution to actually put an upper limit on the diameter of the star, which is what I could have if we upgraded Cherenkov telescopes as intensity interferometers. No, it's just funny that there are these kind of synergies. But yeah, Benito, it's on the ecliptic, not necessarily in the galactic plane. So the confusion is not that enormous.
Miguel wrote the question in the chat, so
do I understand correctly that you need occultations to be able to measure the sizes of stars? If the answer is yes, I understand. The observing mode now with MAGIC VERITAS, especially in the future with CPAs, will be pretty bad, right? And you won't be given time to target sources.
So so there are two things that I explained, which is that we can perform angular measurements with our telescopes as optical interferometers, and then we don't need asteroid occultations. or we can also measure asteroid occultations to measure angular diameters. Okay. The question, are we still doing it? Yes. So we have a proposal in MAGIC that actually allow us to follow these kind of events. How do we do it? As we predict when the occultation happens, then the observing time that we need on those occultation events are few minutes. Okay. So our proposal requires 10 hours of observation per year, and we follow roughly 10-15 events per year. So it's really not a huge time investment. And as you compute when these occultations are going to occur, the investment is really not that high. Also, it is relevant to say that now with Gaia, the actual ephemeridis of asteroids is improving dramatically. Therefore, the uncertainty on the time and on the actual occultations happening at all is really small. Therefore, this science case could be useful to measure the diameter of specific stars. Which ones? The ones that are very hard to measure their diameter through other ways. For example, the very cool stars, the K-type stars, are really, really hard to measure with interferometers. But with this kind of occultations, it starts being possible.
But I think maybe Miguel can correct me if I'm wrong, but he's asking whether you can perform the intensive interferometry observations while performing gamma ray observations.
I mean, you could, but
you have special setup, right? That you need to.
So right now in MAGIC, we can do both very high energy and fast optical observations simultaneously. But when we target these stars, normally there are no interesting very high energy targets there, and these stars certainly are not very high energy gamma ray emitters, and therefore we could perform observations simultaneously, but we are not lucky enough so that these targets are interesting for very high energy analysis. And the time investment that we need is so short, these events last seconds. So most of the observing time that we request is overhead. So it's just repointing there, etc. So it's a very small investment that we lose very high energy observations.
That's a question.
Yeah. So I understand that you are essentially limited now to measure stars because they are bright, compact, and so on. So, but for the next generation of Cherenkov telescope, like for example in CPAO South, provided that we have at least 4 LSTs, the big ones, are there predictions about which limited magnitude you can achieve for sub-milliarsecond resolution? Just to see if, I mean, to know if you are going to be able to observe any of that.
Yeah, so probably you're interested in extragalactic sources, and extragalactic sources very hard. So the sensitivity that we right now estimate is on the 7th, 8th magnitude, and normally extragalactic sources are on the 12th, 13th magnitude, normally in the visible, in short wavelengths. Historically, there have been some lasers that reach relatively high luminosities, but it would be very, very hard to observe such a thing. But there is hope. Why? Because if you actually thought about using intensive interferometry between enormous optical telescopes, you could imagine ELT and VLT doing interferometry together. Classical optical interferometry would be madness, would be so expensive, and these telescopes are not built for that. But with intensive interferometer, you really just need to synchronize signals and fast optical photomultipliers or any photodetector that is ultra fast. So it's perfectly possible. So it's the technology that we are exploring, the one that would allow you to have measurements of the broadline region of lasers and things like that.
But this is only adding larger collecting surfaces on the telescopes, right? If you use
larger baselines. So meaning, the CTA South has the problem that our pixels need to be very large because the optical quality of the mirrors is very large, no? So when you start going to the beyond, for example, the 8th magnitude, then you are the night sky background is already as bright as the signal that you're getting from the stars. So then you're adding a lot of noise, and going beyond that noise is really, really hard. No? But if you were using an actual optical telescope with optical quality, then the 100% of the photons that you would be measuring would be coming from the star. Doesn't matter that you go to magnitude 8 or magnitude 13 or magnitude 15. So the predictions are actually very optimistic when thinking about enormous optical telescopes using intense interferometry, because essentially 100% of the photons would be signal, and therefore it would be much easier to find that correlation.
I was thinking about an alternative. Let me know if it's a crazy idea, but perhaps somebody thought about that before. Imagine a very classical optical interferometer like VLT with a number of Cherenkov telescope like around. Will it be possible to combine classical optical interferometer with intensive interferometer so that you can have the sensitivity and also the higher resolution?
So you can combine them at the higher level, meaning that you can combine observations from one, observation from the other, and they are covering different ranges in the UV plane. But a direct combination of the signal itself, as what you are measuring is different nature, then it's not possible. But something interesting of what you said is, for example, VLTI is made of a system of telescopes, some big ones, some small ones. Now VLTI is exploring to use intense interferometry, as you can do it simultaneously between all telescopes at the same time as a given set of telescopes are performing optical interferometry, combining physically the light beams. So the other optical telescopes on the VLTI system of all the support telescopes, etc., could be simultaneously performing intense interferometry observations for free, because those are simply not used when you choose your array of telescopes for performing optical observations. So intense interferometry observations is something that optical telescopes are now considering of performing, but Cherenkov telescopes have this limit of the they will never go like to 14, 15 magnitude. That is really, really hard to think of. What I would probably see easier is to improve our signal to noise for those targets that we can observe easily. No? So for those stars at 6th or 7th magnitude to reach excellent signal to noise, to really reach to a lot of detail within those specific class of sources. That is something that I see easier technically.
Sorry, a follow-up on something that you said. So you said before that the sensitivity in magnitude is limited by the baseline, by the size of the baseline that we have. So if we were to use, for example, instead of building an array with small size telescopes, building an array of large size telescopes, wouldn't we be able to improve? No, of course it would be crazily expensive, but
no. So sensitivity does not improve with baseline. What I meant is that for reaching good sensitivity with the baselines that you would need for extragalactic sources, like going into the micro-arc-second resolution regime that you would need for extragalactic sources, then the only way to reach the required sensitivity with those large baselines would be classical optical telescopes. But sensitivity for these interferometers is given by the amount of photons that you are able to correlate. So the larger your telescope, the better.
I guess it's increasing the baseline to decrease the confusion.
But the night sky background would be the same for the same pixel.
If the telescope is the same, then our pixels are like this, and that is what fixes them.
0.1 degrees, and you get an amount of night sky background photons.
I believe what you mean is that if two telescopes are very close together and you are observing in fast optical astronomy mode, sorry, this is a mess because it's We are talking about interferometry, about fast optical astronomy. This is hard. So when we are observing in millisecond time ranges, if you have two telescopes that are together, the two telescopes will see the same fluctuations. When you separate them, why the same fluctuations? Because you are observing the same atmosphere, the same convective cell of the atmosphere that is moving slightly a speckle of light into a given direction. If you separate the telescopes enough so that the atmosphere that they see is different, then the noise that they are measuring is independent, and therefore you are statistically reducing it by a square root of n. But in interferometry, it doesn't matter, because the atmosphere is really not adding much of a problem. As you are observing in nanosecond timescales, and you are correlating the time of arrival of photons arriving individually into two different telescopes separated by a given distance, doesn't matter what happens with the atmosphere. The important thing is that photons with the same wavelength arrive exactly at the same time in both detectors. It's very complicated, but it only improves in the case of fast optical detectors.
There is another question from Miguel Pertorre. Could you remind again the limiting magnitude in U to determine stellar sizes?
Can you repeat, sorry?
The limiting magnitude in U to determine the stellar sizes.
In what?
In U.
In U. Sorry, in U. Sorry, in U band. Okay, sorry. So in U or in B, the wavelength that we are observing is 420 nanometers right now. So in that wavelength, what we are now roughly observing is magnitude 4. We can probably go slightly beyond that, okay? So we can probably reach 4.5 with enough observing time. And as soon as we add if we added the large size telescope prototype, and we are able to perform interferometric measurements with it, then we are expected that to improve by a unit at least. So this means that in the short time scales, we will reach roughly magnitude 5 or even magnitude 6 with LST. The grant that I got is to equip the 4 future LSTs. This means that when we start correlating a large size telescope with other large size telescopes, we again expect to improve another magnitude. Therefore, we are starting to reach the 6-7 magnitude range that starts being much more attractive, because it starts being comparable with CHARA. But remember that we are performing correlations between each telescope versus each telescope. Therefore, the number of correlations is n times n-1 divided by 2, which is a high number of correlations.
Last one.
I have 2 naive questions. Only one. Why do you have a W shape there in the occultation instead of a classical box shape?
This is diffraction, pure diffraction. So the light from stars is roughly a laser, no? So you have a laser, and the Kuiper belt object is tiny, actually smaller than the actual disk of the star, no? So essentially, what is happening is that the diffraction pattern from ingress is mixing up with the diffraction pattern of the egress. It's a mess of Bessel functions, and then it also depends on what is the offset between the object and the star, and these shapes change a lot and also change with wavelength, etc. The interesting thing about this, I will just use your question to say something fun, is that by measuring this, we know at which distance it is, independently to its size. So this means that if we are actually able to reconstruct nicely the diffraction pattern, there is no question that what we are observing is a Kuiper belt object. So the doubts on these measurements coming from these guys here that the community does have would be vanished. But if we see nothing, then it would be the upper limits that we would achieve here are strong, and therefore what I believe is that we would be able to essentially reject some of these observations.
The very last one is I'm not familiar with this kind of telescope, so I don't know which is different between the different channels that you were showing, because you showed that there are 4 different channels.
4 telescopes.
Because okay, each channel is for each telescope. Okay.
Yes. So it's not like hypercam that you can
Yeah, I was thinking about that,
simultaneously.
exactly.
Yeah.
Okay.
So actually, 2 years ago, I submitted another ERC proposal that I did not get, and in that one, I was going way more aggressively, suggesting that what we could do is to have several colors, doing something similar to hypercam, like with dichroics separating the optical beam and throwing the different wavelengths to different pixels. No, so then we could have shapes like this one for different colors. And when you have that, then it's very interesting because the diffraction pattern changes with the wavelength. So you can do very interesting stuff when you have that. No? So yeah.
Thank you.
Okay. So there is nothing else. Thank you very much again, Tarek, for the presentation.
Shall I close this?
You can.
Okay.